The two-factor analysis of variance that we take up in the next few chapters is complex in terms of its calculations, but really is not so difficult to understand in terms of its logic. In this course, we let Excel or Google Sheets do the calculations, so it's most important that we understand the logic, and that's what we'll look at in this short video. Our one-way analysis of variance allowed us to look at more than two groups, but they were defined by a single independent variable. It might be something like your race or ethnicity that's not experimentally defined, or it might be 3, 4, 5 treatment groups, but all focusing on just one independent variable that would define the groups. Our factorial ANOVA allows us to look at two or more factors as independent variables in a single experiment with one dependent variable. So for instance, if we were considering a way of measuring Carol Dweck's growth mindset not as just fixed or growth, but a continuum that went from fixed towards more of a growth design, we might do what she did in her experiment, where she had two different treatment protocols. One of them included the growth mindset information, and the other one, if you remember, was just teaching study techniques. But she was looking at a single age group of students. It would be possible to look at, say, young people, perhaps people of grade school age, a middle-aged group, maybe college students and young adults, and then an elderly group, and see whether these different treatment protocols were more or less likely to change their growth mindset within the different age groups. So this baseline experiment with two factors would have two independent variables, the two types of treatment and the three age groups. As an experiment, we would be designing a 2 by 3 design, and just like 2 by 3 when you're talking about area, it's going to come out to be a total of 6 groups. So we would have the young school-age children, the middle-aged or middle adult, and the elderly people, and then we would be looking at whether they got the control group or the growth mindset group. And if we designed an experiment that had 100 people in each of these conditions, we would need a total of 600 people to carry out this study. We would have a total of 300 in the control group condition and another 300 that got the growth mindset, and it would take 200 within each age group to carry it out. So you can see that as the number of factors and within each factor the number of groups grows, it means that we need an increasingly large sample size in order to be able to test the factors. Our two-way analysis of variance has a number of components and then ends up yielding a number of parts in the results, so it's worthwhile to list them and look at all of them. We have just one dependent variable. It's measured at the interval or ratio level. We were looking at the possibility of measuring mindset from fixed to growth along a continuum. And if you remember the test that was available 2 weeks ago, it asked a large number of questions, and that would let us develop exactly this kind of interval or ratio level variable. We have two independent variables. They're usually nominal variables, whether you got the control treatment of just study skills methods or the study skills methods plus the growth information. Sometimes we have an independent variable where something that was originally ratio has been clustered or grouped. In the situation with the age variable, if we had age year by year, it would be a ratio variable. But when we talk about young, middle adult, and elderly, then we've got a grouping variable that's been made out of the original ratio variable. We end up having 3 hypothesis tests. We test each of the 2 independent variables controlling for the effects of the other independent variable. So our first hypothesis test might ask whether our treatment type, getting the study skills method alone or the study skills method plus the growth mindset information, does that have an impact on your outcome of ultimate mindset? The second test looks at the impact of being in the age groups. Does, regardless of the treatment you receive, does the age group have an impact on the outcome of the mindset that you have? And finally, our analysis of variance looks for an interaction. It may be that one or another of the age groups is either particularly able to grasp the mindset information or perhaps particularly resistant to grasping the mindset information. And so there may be an interaction between the treatment and the age group. Our two-way analysis of variance is a two-stage procedure. The first stage is just like what we did in our one-way analysis of variance. We would compute a sum of squares total that represented all the variability within the data set, and then we would break it into the components, the part that was variability within the treatment groups. If you remember in our example, we were thinking of having 6 treatment groups, but within those groups, defined by both age and which type of treatment they received, within the groups, the variability would be due only to error or random factors. And then there would be the variability that was between the groups due to, in this case, 2 different independent variables. So in stage 1, we break out just the random part compared to the systematic part. In the second phase, we take the differences between the groups, the variability that's due to the treatments, and we analyze that or break it down into a component that's due to factor A, perhaps which treatment they received, another bit that's the sum of squares or the variability due to factor B, the age group, and then the possibility that there is some kind of interaction, some combination of age group and treatment that might be especially different. And so we would get a F test for factor A, an F test for factor B, and an F test for the interaction of A with B. This rather daunting looking slide shows us how we eventually arrive at our 3 F tests. One of them is looking at the row variable, in this case our treatment groups. One of them is looking at our column variable, in this hypothetical case our age groups, and a third one at the interaction. You can see that the same mean square within shows up in the denominator of each of those F tests, and we'll compute it the same way as we did in our one-way analysis of variance. The sum of squares that's within treatments will be divided by its degrees of freedom to give us a mean square within. Our degrees of freedom for within will be the number that we would have for each treatment. We can visualize our situation by redrawing our factorial design. We had 2 types of treatment, a control group and the growth mindset group, and we had three types of people: the young, the middle adult, and the elderly. And within each group, we were thinking we might have 100 people. So that would mean within each of these cells, there would be 99 degrees of freedom inside the cell. So our degrees of freedom for within treatments would be 594. And our total degrees of freedom would be our 600 people minus 1, 599. So that lets us know that in a one-way analysis of variance situation, there would be 5 degrees of freedom, and in fact, that's the number of cells, 6 cells, minus 1. And those degrees of freedom will be split up, the number of rows minus 1, so here that would be 2 minus 1 is 1. The number of columns minus 1, that would be 3 minus 1, or 2. And then this number that we get as the total number of cells, minus 1 is 5, minus the degrees of freedom used for the two factors, that would be 5 minus 3, leaves us 2 degrees of freedom. We would go about computing our degrees of freedom across the rows to give us a sum of squares for the rows. We have another set of computations for doing the sum of squares or variability within the columns, and then the interaction would be the variability left over. It is a sort of a complex situation. We are not going to do these computations of the actual sums of squares by hand, but once we have the sums of squares calculated, it's not so tough to do the degrees of freedom, and then just as we did before, to divide across the sum of squares divided by the degrees of freedom to get the three different mean squares, and then each of those mean squares using the same error degrees of freedom in the denominator will give us the three different f-tests. Going back to our more conceptual drawing, we're seeing that we'll take our original sums of squares total and divide it into two parts, which is what we were doing earlier with our one-way analysis of variance, and then we break down in the second stage the sum of squares that was between groups into parts related to the two factors and the interaction. And then our mean square, when we average that across degrees of freedom, compares the interaction relative to the error or random variability, the treatment factor B, that would be our age groups, and the treatment factor A, that would be our different treatment groups, each of them being compared with the same sum of squares within divided by its degrees of freedom. Our ANOVA table quizzer lets us work with these factors and get familiar with them just as it did with the one-way analysis of variance. You have to set it for a two-way ANOVA. It gives us the three elements: row, column, and interaction. It gives us error and then total. So in this situation, we would have to find our degrees of freedom for rows by taking 979 dividing by 589. My guess is that's going to show up to be 2. And then we'll be able to figure out our degrees of freedom error by adding up 2, 4, 8, and that gives me 14. That must mean I'll have 15 degrees of freedom error left over. I could add up all of my sums of squares and get my sums of squares total. Going across, I would take 1382, divide it by 4, and I would get my mean square here. I would then, and I can see that that mean square, whatever it is, divided by the 72, that's my mean square within, generates that f-test. Here, when I go I've done my mean square, I would divide by 72, and that would generate an f-test there. So there's more components in the ANOVA table quizzer, but you can see that it works in exactly the same way. What about our hypotheses that we're testing? Just as we had in the one-way analysis of variance, we do have a null hypothesis, but we need a null hypothesis for each of the 3 analysis of variance f-tests that are being tested here. So one set of hypotheses looks at whether the mean in group A1 is the same as the mean in group A2. Our null hypothesis would be yes, they are the same. Our alternate hypothesis would be that they differ. If we had only 2 groups for B, we would be hypothesizing that they were equal, or alternatively that they were different. If we have 3 or more groups, our null hypothesis says that all of them are equal, but we can't state our alternate hypothesis for more than 2 groups as a single equation because we don't hypothesize that all of them differ from each other. We just hypothesize that at least one differs from each other. I've used the phrase control several times, saying that I'm looking at the impact of one factor controlling for the impact of another factor. It's not the same as an experimental control. In statistical control, we're looking at the effect of one independent variable within each group of the other independent variable. So for instance, if I look at the impact of age, I'm going to say for everybody who got the control treatment, there were 100 in each setting, within the control group, do I see differences by age? And then I would look within the treatment group, in the case that people who got the growth mindset information, I also have 100 of them in each group, and look to see, am I finding differences by age within that treatment group? And so I'm able to say whether they're age differences because I've controlled by only comparing people who all got the same control treatment or people who all got the same age treatment. The same thing can be done looking at within the age group, did they get the growth mindset or did they only get the control group? Within the middle adult group, within the youth group, did I find people a difference with the treatment group? So because I'm only comparing people who had either the same age and got different treatments, or they got the same treatment and different age, I'm statistically removing the impact of the other independent variable. And it often occurs that a variable that was not significant in a one-way ANOVA may become significant when another variable has been controlled, and that is the reason for the power of a factorial analysis of variance. Our null hypothesis for the interaction is simply that there is no interaction, and the alternative hypothesis is that at least one combination of factors A and B has an especially strong or especially weak outcome, and neither of these can be stated as equations. So we can see that our logic will be to test 3 null hypotheses. One main effect in the row. Does factor 1 have any impact on the outcome? In this situation, are the groups defined by factor 1, the getting the control or the growth mindset intervention, do they have any impact on the ultimate mindset in the group? Similarly, I look at the columns. This would be the groups defined by factor 2, or our age groups, and then finally the interaction effect. So I will be doing all 3 of these f-tests within one set of analyses. The important part to take away from this emphasis on the logic is the fact that we have a 2-stage design. The first one is like the one-way analysis of variance that breaks out the systematic compared to the random components, and then in the second stage breaks the systematic components down into the parts that are related to the two factors, those are main effects, and then to the interaction. In the next video, we're going to look at some actual data that was developed by the Texaco Oil Company back in the 1970s. They were beginning to look at ways to reduce air pollution from car exhaust, and they developed a new octal filter that could be put on the exhaust system. This was before the invention of catalytic converters, and some people worried that it was going to make cars noisier. So Texaco Oil looked at a total of 36 cars. It was a fairly small study, and they had them divided by small, mid-size, and large. And within each of those groups, there were 12 cars. And those 12 cars were split so that 6 of them would get the standard filter and 6 of them would get the new octal filter. So you can see we've got type of filter as a row variable and size of car as a column variable. And in the next video, we'll look at the results from carrying out the analysis of variance using that Excel data analysis tool pack, or in Google Sheets using the Excel Miner tool pack. Once we understand this logic of the two-way analysis of variance, it isn't so hard to deal with all of the components that come out of the analysis tool pack. So let's move on and see what it looks like to deal with an actual set of data.